article derive the Gauss's formula for the r11, r12 and r22. Solution: at any point P on the surface there are three independent vectors n r1 and r2, so that the every vectors at P can be expressed as a linear combination of these vectors. We know that L and N are the resolved parts of r11, r12 and r22 along the normal to the surface. Therefore, we may write r11 equals to ln plus L r1 plus lambda r2, r12 equals to mn plus m r1 plus mu r2, r22 equals to nn plus n r1 plus mu r2. Equation 1. The equation 1 are known as the Gauss's equations or the Gauss's formula, and the coefficients of Lmn, lambda mu and nu are called as Gauss's coefficients or the Christopher's symbols. We shall see that these coefficients are functions of E, F, G and their partial derivatives with respect to U and V. Since R1 equals to Ln plus Lr1 plus lambda R2, taking the dot products of the both sides of the above equation by r1 and r2, we get r1 dot r11 equals to L r1 dot n plus L r1 dot r1 plus L r2 dot r1, or r1 dot r11 equals to EL plus F lambda. Equation 2, because r1 dot n equals to 0, r1 dot r1 equals to E and r2 dot r1 equals to F, or r2 dot r11 equals to L r2 dot n plus L r2 dot r1 plus lambda r2 dot r2, or r2 dot r11 equals to FL plus GL. Equation 3, because r2 dot n equals to 0, r2 dot r1 equals to F, r2 dot r2 equals to G. Now r1 dot r11 equals to 1 upon 2 del over del u of r1 square equals to 1 upon half del over del u of E equals to half E1, and r11 dot r2 equals to del over del u of r1 dot r2 minus r1 dot r22 equals to del over del u of F minus 1 upon half del over del V of r1 square equals to F1 minus 1 upon 2 del over del V of E equals to F1 minus 1 upon 2 E2. Putting these values of r1 dot r1 and r11 dot r2 in equation 2 and 3, we get 1 upon 2 E1 equals to EL plus F lambda, and F1 minus 1 upon 2 E2 equals to FL plus G lambda, or EL plus F lambda minus 1 upon 2 E1 equals to 0. Equation 4, and FL plus G lambda minus F1 minus 1 upon 2 E2 equals to 0. Equation 5, solving 4 and 5 for L and lambda, we get 1 upon minus F into F1 minus 1 upon 2 E2 plus 1 upon 2 E1G equals to lambda upon minus 1 upon 2 E1 F plus E into F1 minus 1 upon 2 E2 equals to 1 upon G minus F2 equals to 1 upon H square, or L equals to minus F1 plus 1 upon 2 F E2 plus 1 upon 2 G E1 upon H square, or L equals to 1 upon H 1 upon 2 H square into G E1 minus 2 F F1 plus F E2, equation 6, and lambda equals to minus 1 upon 2 E1 F plus E F1 plus minus 1 upon 2 E E2 upon H square, or lambda equals to 1 upon 2 H square into 2 E F1 minus E E2 minus E1 F, equation 7. Now to find the values of the M and mu, taking the dot products of the both sides of the equations, r12 equals to m n plus m r1 plus mu r2 with the vectors r1 and r2 respectively, we get r1 dot r12 equals to m r1 dot n plus m r1 dot r1 plus mu r2 dot r1, or r1 dot r12 equals to e plus em plus f mu, equation 8, because r1 dot n equals to 0, r1 dot r1 equals to e, and r2 dot r1 equals to f, and r2 dot r12 equals to m r2 dot n plus m r1 dot r2 plus mu r2 dot r2, or r2 dot r12 equals to fm plus g mu, equation 9, r1 dot r12. Now r1 dot r12 equals to 1 upon 2 del over del v of r1 square equals to 1 upon 2 del over del v of e equals to 1 upon e2, and r2 dot r12 equals to 1 upon 2 del over del u of r2 square, 1 upon 2 del over del u of g equals to 1 upon 2 g. Therefore, the equation 8 and 9 becomes 1 upon 2 E2 equals to EM plus F mu, and 1 upon 2 G equals to FM plus G mu G, or EM plus F mu equal minus 1 upon 2 E2 equals to 0, equation 10, and Fm minus mu G minus 1 upon G1 equals to 0, equation 11. Solving 10 and 11 for m mu, we get m upon minus 1 upon 2 f G1 plus 1 upon 2 E2 G equals to mu upon 1 upon 2 E2 f plus 1 upon 2 EG 1 equals to 1 upon AG minus F square equals to 1 upon H square, or M equals to 1 upon 2 H square into GF2 GE2 minus GFG1, equation 12, and mu equals to 1 upon 2 H square into EG1 minus FE2, equation 13. To find the value of the N and mu, since r22 equals to n plus n r1 plus mu r2, taking the dot products of the both sides of the above equations with r1 and r2, we get r1 dot r2 equals to n r1 dot n plus n r1 dot r1 plus mu r2 dot r1, or r1 dot r2 equals to en plus f mu, equation 14, and r2 dot r22 equals to n2 dot nr2 dot n plus nr1 dot r2 plus mu r2 dot r2, or r2 dot r22 equals to fn plus g mu, equation 15. Now r1 dot r22 equals to del over del v of r1 dot r2 minus r12 dot r2 equals to del over del v of f equals to 1 upon 2 of del over del u of r2 square equals to f2 minus 1 upon 2 g1, and r22 dot r22 r2 dot r22 equals to 1 upon 2 del over del v of r2 square equals to 1 upon 2 of g2. Therefore 14 and 15 becomes f2 minus 1 upon 2 g1 en plus f mu, and 1 upon 2 g2 equals to fn plus g mu, or en plus f mu minus 1 upon minus f2 minus 1 upon g1 equals to 0, equation 16, and fn plus g mu minus 1 upon 2 g2, equation 17. Solving 16 and 17 for n and mu, we get n equals to 1 upon 2 g f g2 plus g into f2 minus 1 upon g1 equals to mu upon minus f into f2 minus 1 upon g1 plus 1 upon 2 eg2 equals to 1 upon eg minus f2 equals to 1 upon h square, or n upon 1 upon 2 fg2 plus gf2 minus 1 upon 2 gg1 equals to mu upon minus f2 plus 1 upon 2 fg1 plus 1 upon 2 eg2 equals to 1 upon h square, or n equals to 1 upon 2 h square into 2 gf2 minus gg1 minus fg2, equation 18, and mu equals to 1 upon 2 h square into eg2 minus 2 f2 plus fg1, equation 19. The equation 6, 7, 12, 13 and 18 and 19 gives us the values of the Gauss's coefficients in terms of the EFG and their partial derivatives.